So, hello everyone. I must apologize for my voice, but I couldn't skip the opportunity to moderate this session. So we are heading up to 15 years of RISC-V at this point, and we're starting the session with the State of the Union by Krste, celebrating those 15 years and showing us what direction we will be heading. So RISC-V is very much in AI, has multiple matrix extensions coming our way. And as the TSC Vice Chair, I was there at the moment when we got that work started, when we got it underway. And in addition to that, there is real-time extensions for interrupts, hyperdimensional vectors, all in this very exciting session. And without further delay, I'd like to introduce Krste Asanovic, our Chief Architect at RISC-V, with the State of the Union.
Okay. Can you use this microphone? Hello. Great. Hello, everybody. It's great to be here in Paris. It's been a little while since I've been here. Wonderful city to visit. So, State of the Union. How is the State of the Union? Well, the State of the Union is strong. Some you may wonder, what do you mean by State of the Union? I mean, this whole group, the whole community working together to push RISC-V forward. We've been doing very well. Things are going extremely well in RISC-V land. What do I mean by that? Well, we're solidly established in the embedded space. We're on the verge of this widespread adoption in application processors, and I'll talk a bit about that. We are really the standard base for new AI accelerators. But I think the other thing I want to mention now is I'm starting to see across industry, everybody realizing that, oh, RISC-V is the only viable thing going forward in the future. So the pennies are dropping as people see what's happening across the landscape, the kinds of platforms you want to build, the developments going on, and people are sort of realizing, oh, we have to align with RISC-V because it is the future, right? Now, different industries, different verticals will have different timelines, but everybody's now, the penny is dropping, people are seeing, oh, this is what RISC-V is going to be doing, and we have to have a plan to work with RISC-V. So we're 15 years old, so the official birthday is on Sunday, May the 18th. And we decided this was the official birthday because this was the day that Andrew Warneman sent an email to me saying, okay, I give up, we should do a new ISA. He was a graduate student at the time and wanted to avoid all the work that's involved in building a new ISA, but we finally realized we really had to start from scratch. And so that was the day we picked for the official birthday for RISC-V. So it's been 15 years, and I thought it'd be good to go back and try and think about the last 15 years. And I kind of roughly divided it into 3 5-year phases. The first 5 years were really the initial development at Berkeley and, just experimenting, trying things out. We went through many, many iterations, many different design choices, many different tape outs. And then at the end of that 5-year period, we started rolling it out to the broader community, including the big event, going to Hot Chips, wearing these T-shirts and telling everybody they should use RISC-V. I made a really good reception. The next 5 years was really about the initial standardization. So at Berkeley, we developed these specifications, but now we needed to build the bigger community, go out and say, are you okay with these specs? And so there was some relatively small changes, but engaging with the broader community, with a lot of companies, setting up the foundation, which is now RISC-V International, and agreeing on, for example, for the first Linux distros, we're going to use RV64GC. So this next 5 years was really engaging with the broader community, starting the standardization effort, and really enabling the ecosystem to begin developing. And also in that period, we had the first commercial offerings, the first silicon, the first IP, coming out from various vendors. And so over the last 5 years, we're seeing this widespread adoption in embedded systems, and we've sort of been filling out the standards. And I think a big milestone was RVA 23, which we ratified last year, which really defines a very full-featured, general-purpose instruction set for application processors. And that really is going to be a foundation for a lot of the big ecosystem work that's coming on. And as well as this effort, we've also been building out the foundational software, the Linux ports, the compilers, everything else we need, the libraries, to build a good solid base. So what happens now? Now, one thing is we didn't have these 5-year plans. We didn't sit down there and plot all this out. We worked together with everybody very dynamically, moving forward over time. But looking back, I thought these were a good way of breaking up the last 15 years. So what's next? Well, I think what we're seeing is RISC-V in places where there is not a large software ecosystem demand. It's very easy to move to RISC-V, and that's been happening. Where there's a large software ecosystem demand, we need to be more specific and move into these industry verticals. This is a theme from several of the speakers this morning. I just want to emphasize this. So in this early phases, we built the initial ISA, and now we've been developing the foundational software, bringing up everything so most things can be ported relatively easy to RISC-V. But now we're in this phase where we're really trying to move into a lot of these different verticals. Everything from embedded to space to HPC to TVs, whatever. There's a lot of verticals. I just highlighted a few, but there's really many more. Now, one of the key things in these vertical markets, they want a complete solution. They don't want a piece of the story. And so what we're going to be doing in RISC-V, I think what you're seeing over the next 5 years is in each of these different verticals, there'll be a more focused attack in terms of providing everything that's needed to really satisfy what people need in each of those areas. And so I just want to talk a little about, across our community, we'll have different groups, different special interest groups, working groups, trying to work on each of these verticals. But I just want to put that in context of the broader standards development, what we need to be doing. So we have this common ISA and foundational software as the baseline that enables you to get going in any one of these areas. But it's really important to work with the software ecosystem partners in each of these verticals. Like, what do they need? What are their gaps? How does it work? They need to be involved and engaged. And this work we do at RVIA, organizationally, we have the SIGs, which are for members, special interest group, but we also have joint working groups where we can work with non-members who may, for various reasons, not want to be part of RISC-V, or maybe their structure doesn't allow them to join as a member. But they're important ecosystem partners. We need to work with them to figure out what software they need, what we need from RISC-V. Now, the first step is really, I've seen this many times, is people say, oh, RISC-V doesn't work in this area. And what that means is they did an initial port and something broke or something was lower performance than needed. And the knee-jerk reaction was got to go fix RISC-V. A lot of the time, though, there's a bunch of work needed just to port and tune code to work with RISC-V if it's never run on RISC-V before. And that's a necessary first step before you start asking for changes at RISC-V. Go look at the code, do the porting, figure out how to make it work well in RISC-V with what's already there. So before coming back and saying there's all these needs, first you really have to get the existing code base ported over to RISC-V, working as well as it can with our existing infrastructure. At that point, though, you may still see there are gaps or even opportunities where RISC-V is doing particularly well in some domain. And the other thing is, as I emphasize again, each of these verticals really wants a complete solution. It's the worst thing we can do is have 90% of the solution for 100 markets, right? It's much better to have 100% of the solution for 10 markets than the other, right? Because the customers really want everything they need in each of those markets. And at RVIA, if those different verticals need a lot of support in new standards development, we're really going to have to prioritize because we can only move so fast in building standards in a coherent way. And so this is one of the jobs of the TSC, guidance from the board of directors, in prioritizing these key areas that we're going to go work on and make sure we complete and finish so our members can be successful in working in these verticals. Right, so please respond to the TSC, the BOD, and others asking for what you need, what are the priority areas that you see, so we can help allocate our bandwidth appropriately. The last thing I'll say, though, is, and this is important, all these different verticals, if they work in a silo, there's a risk of creating a very fragmented RISC-V, where there is a automotive RISC-V, a HPC RISC-V, a blah, blah RISC-V. That's not really a very effective way to work, and it's not going to allow us to have the best solutions. It's important that we look at what the verticals need and figure out the components that can be shared across the whole space or a substantial number of other applications in the space. It's our job at RVIA to build the standards in a way that we build these modules that are reusable across different domains, because that will give us the best results, because we'll have good software support for each module, and if you need that in a domain, good support will be there, versus if we try and build very specialized things for each domain, but there's just not enough engineer resource in the world to make all of that work well. So we really have to find the commonalities across all these verticals and emphasize that to maximize the best use of our resources, okay? So we do need to make sure we complete everything a vertical needs, but do it in a smart way where we're investing in common technology that we use across all the other verticals that we will eventually be tackling. Because RISC-V will take over everything eventually, right? That's part of the plan. Okay, so profiles. So just want to shift gears a little, talk about profiles. So we've already ratified a few profiles. I just want to talk about, people have been asking about the next steps in the application process of profiles. So RVA 23 was the last major release that we did for the application process of profile. And the model we have is until the next major release, we will be doing minor releases, but the minor releases will only have options. So there'll be some new options added, and the goal is for the minor releases to be roughly once or twice a year. And that's just updating the documentation, the spec, and saying, here's the profile, here are the new options that are part of the profile, and categorizing those options. Are they a development option, expansion option, etc. So those will happen more frequently. The next major release, we've tentatively named RVA 30. And RVA 30, we're planning not to do that for a few years. We've just released RVA 23. It's going to take time for the ecosystem to digest that and build on that. Also, we want to make sure the next major release, which is going to have significant new mandatory features, that those are a significant step up in capability. Otherwise, there's no reason to move there. So RVA 30 will be a major step up in features, but it's going to take us some time before we get there, right? So think of it as a few years' time before RVA 30. On profiles, we focused on the application processors as they have the biggest, richest ecosystem and rely on binary distribution. So it's the most important ones to have profiles defined. But we're also seeing increasing enthusiasm to define something in the microcontroller space. So we have a very early draft of RVM profile, but really need to work harder on that. So that's going to be a theme, I think, pulling together folks interested in embedded, the toolchain providers, debuggers, everybody else, to work on this standard ISA profile and possibly a platform as well. And also in automotive, there's a lot of interest in an automotive MCU profile. So another thing I want to mention is there's been a lot of improvements in specifications. This is a lot of work by a lot of people who've been working very hard in pulling together the ISA documents and trying to make a more unified, standardized ways of building everything. You can go check this out at GitHub. And the goal is to get everything into a common repo where the database is there and we can generate all the different forms and materials we need from that specification, from the contents of that repo. There's still a lot of work to be done. A lot of work has been done. There's a lot more work to do. There's a documentation SIG. We'll be starting up a unified database SIG as well, and the GitHub repo. So those are places to go and help work on improving the documentation. If you're not happy with the status of documentation, please contribute and go work with those teams on making it better. But the big news is we just released a new cleaned up version of all the specifications. If you go to the website, it should be up now. And in these versions, what we've done is removed everything that is historical and non-ratified. So the specs now are clean in that they only have, the published specs have only the ratified content on them. So it's a big milestone. Thank you everybody who worked hard on this. And so the version is the May the 8th version, 2025. And this, I think, is the first time we've published a single spec that is only the ratified components, but all of the ratified components in there. So please go check that out. And again, contribute to the documentation effort. So now I have a few slides talking about some of the extensions in progress. I just picked some. There's more than I could fit in a short talk. So we have some new security extensions. I just want to highlight these so people are aware they're going on. This one's actually been going for a little while. It's the supervisor mode PMPs. And this is designed for sort of real-time OS supervisor mode to allow protection between that and the user tasks. And this is now advancing. It's sort of stuck for a while, but now there's real energy going in, and this seems to be making progress. RISC-V Worlds, previously known as WorldGuard, this is to provide secure partitioning of an SoC, sort of boot time. This is now proceeding as a fast track. Supervisor domains, this is for bigger systems that use a memory table memory map table to separate different supervisor domains. One of the applications is confidential computing, but this can also be used for lower-end systems for embedded, more flexible partitioning than the PMPs give us. That's also moving along. So Cherry, we've done a lot of work with the Cherry task group with the Architecture Review Committee on sort of organizing the specifications. So one thing I'll highlight is, as we look through the specifications, we realize that Cherry really represents a new base architecture. So along with RV32i, RV64i, RV32e, RV64e, we now have RV32y and RV64y, the Y for capability. So as the work is going on, we're restructuring the Cherry specs, and they seem to fall in nicely once we adopt this model, that Cherry is really a new base, and it will be adopting, it'll be impacting all the Cherry view of all the extensions is a thing we have to work through as we do this. There's a group working on lightweight memory tagging, and there's a lot of work on additional crypto, including post-quantum crypto. Okay, so a lot of work on security. I want to highlight DSP extensions. This is sort of resurfaced as an important area for RISC-V. Again, RISC-V is taking over every core in every system, including those DSPs. And so one thing I'm happy to report is the P extension, the PAC-SIMD extension, is making progress. It's been a long time in development. Thank you to Andes for the original contribution of this specification. But now we've been making real progress. So this, to remind you, this provides fixed point and integer operations on packed 8-bit, 16-bit, 32-bit, and 64-bit integers in the integer registers. And there's over 100 new instructions, so it's quite a large extension in terms of instruction count, but it will be relatively small in terms of gate count for the processors it targets. So that's moving ahead quite fast. We're also seeing interest in adding DSP functionality on top of the vector extension. So for bigger cores that have a whole vector unit, we want to improve the support for fixed point and DSP operations inside the vector engine. And so there's a new proposal going through for a task group to provide vector DSP. Another topic is long instructions. So RISC-V, we included variable length instructions from the very beginning. And this was just looking ahead. What we saw was there was a need for, one reason was for compressed instructions. We wanted to add 16-bit naturally into the ISA without requiring a different ISA mode or something. It should be just naturally built into the ISA as an extension. That's one goal. But the other goal was looking ahead. We saw RISC-V, we wanted it to be a long-term successful thing. We wanted to provide lots of extensions and lots of instruction space. And, you know, it's a ISA that's supposed to last indefinitely. It's not going to go away because of some business model change. It's going to be around for a very long time. And a fixed 32-bit instruction set is really a barrier, would be a barrier to that long-term evolution. So when we designed RISC-V, we designed in variable length from the very beginning because we knew to last for a long time, you need to support many more instructions that will fit in a fixed 32-bit encoding. And you're seeing this already. The other ISAs are 32-bit fixed with encoding. They're running out of room and having to add, you know, architectural prefixes and other things to expand the opcode space. So another thing to say is, as well as just giving you more space, the longer instructions can help with code size by compressing the bits needed to represent common sequences. They can improve performance, and we're going to need this extra opcode space to support all the growing number of operators and data types that we're seeing as well. So this task group is being formed to formalize the encoding and define the first few instructions with a greater than 32-bit instruction length. Right? So this is coming down the pipe. Let's talk about AI. So last section here, I want to talk about AI. Hot topic. Everybody's thinking about this. I want to think about AI. So it's really pervasive, but it's both as a horizontal technology where AI is infused into applications everywhere. Right? So any device, there's probably some AI going to be needed. And also a single device may run hundreds of different models. Right? So if you look at your smartphone, it's probably have dozens of different AI models now, today, that are being run at different points for different applications on your phone. But there's also, AI is also kind of an application where there are dedicated racks of machines used for training and inference, just purely running AI, right? So you can view it both ways. The common features of AI computing is large amounts of numeric computation on small specialized data types, a large memory footprint to hold the model, and large memory bandwidth to move that model parameters around and to communicate between the different layers. These are kind of common things when you want to do AI well. So AI, though, is a moving target. It's continually evolving very quickly. So it's a very rapid evolution. There's new algorithms, new operators, new data types. Hardware's got to be flexible. The software is changing much faster than the hardware can be redone, right? And people repeatedly get tripped up building some custom AI accelerator and realizing it doesn't work for the next year's algorithms, right? One example is, most of the current models read all the weights on every inference. But what you're going to start seeing is more complex models that are more selective. And they're using runtime selection, dynamic scheduling, of which parts of the model are going to read out to do some inference. And so this is going to need more complex control and scheduling. So the AI model execution is going to get more complicated over time. You can just see that happening. It's just natural the way things have to go to make these big models efficient, right? So with RISC-V, one thing to say is we've designed it as a general computing model, but it allows this balance of scalar, vector, and matrix capabilities in the one ISA, right? So you don't have to switch between different kinds of cores to do different kinds of operations. And as the models get more complex, this is going to become increasingly an overhead for the other competing architectures, right? So the same processor cores can run the non-AI portions of applications as well as the AI portion, which really simplifies the software model, reduces latency, increases utilization, is generally a good thing. At RISC-V, you can scale to any performance level you want. It's just how many cores you put down, the interconnect fabric that you build in the system. And another aspect, because it's a generally programmable system, these new models are run reasonably well on older versions of RISC-V hardware over time. That's a nice property to have. If you have a general processor that has good scalar performance, good vector performance, some matrix performance, whatever the new models are, they're going to run okay on the older RISC-V hardware, and it'll be relatively straightforward to bring them up, right? But what is going to be possible is for different choices, different balances of scalar, vector, matrix are possible while keeping the same ISA. So whether that's in one generation, you have different application design points, where some may not warrant a matrix engine, some may want a very large matrix engine, or across generations over time, you're going to want to change this balance as the model needs change. You can do all of those, that mixture of scalar, vector, matrix. You can rebalance as you need to without changing the programming model, without changing the ISA. And that's a very powerful part of RISC-V in this AI world. So just some things that are going on. So we have been adding additional support for bfloat 16 into the vector arithmetic units. And also there's a proposal through on how to handle FP8 through conversions. But there's going to be a lot more activity in these small data types as they evolve. And one thing to say is these data types seem to come and go very quickly. So we have to be a little careful in which ones we support and how we support them in the architecture. We don't want to be left with several hundred instructions that are no longer useful in this space. So we'll be carefully picking these out. Okay, let's talk about RISC-V matrix extensions. This is the most lively part of RISC-V standards development this year, I think. So one thing to say about MapMol is these provide very large speedups on a key kernel in AI applications, right? It's not everything in AI, but it's an important component in AI. Now, the thing is, if you look across this universe of RISC-V implementations from very small microcontrollers to supercomputers, and also if you look at the different usage needs, are you doing inference? Are you doing training? Am I running this kind of model, that kind of model? Different matrix multiply microarchitectures might make sense, and they may be different enough that different ISA control might make sense. You may want different kinds of ISA depending on the kind of mapmols, size and shape and type of mapmols you want to do. Or you may not need a mapmol at all because it's not important. The performance isn't needed. Okay, so this is kind of difficult, like, oh, this is a very large design space. We may have many different ways of doing mapmol. On the other hand, the good news about matrix multiply, there's only a few operations you can actually do. So in terms of the number of functions you need to support, it's it's orders of magnitude smaller than, for example, for the vector unit, right? There's many few operations that really benefit from matrix multiply instructions. So you're talking dozens of functions rather than thousands in this space. So it's kind of easier for software to handle different implementations of a relatively small number of functions just doing matrix multiply, right? Now, this is a busy slide. So I put this together to try and, as we were developing this, a lot of interest. I think, we have many tens and over 100 or so people participating in the task groups looking at matrix extensions, coming from very different viewpoints, shapes and sizes of systems. And so kind of what we realized looking across the space, we had 2 task groups that were running, but really we had 4 approaches that were being pursued by different members in the community. So we just wanted to take some time to pull apart these 4 approaches and give you a sense of what's happening there. So going from left to right across the screen, your left to your right across the screen, going from smaller to bigger implementations generally. And the first 2 on the left are matrix extensions that don't rely on additional matrix state. They just reuse the existing RISC-V vector registers. So the original IME task group, which was started up a little while back, the aim of that group was figure out how well you can do a matrix multiply without adding new matrix state, just using vector registers. And really, over the course of discussions in that group, a few approaches, general approaches kind of emerged. The one on the extreme left is very simple, doing dot products using vector registers. And this one actually, is, if you look at the microarchitecture diagram underneath, is really more of a vector extension. It's just adding to the vector unit the capability to do one or a few dot products out of the vector registers directly. And so we're kind of considering that not quite a matrix solution. It's really a vector extension. So that is going to be handled as a separate vector extension, sort of outside the main matrix arena, right? The next one over is what a lot of folks in the IME task group were interested in, which was reformatting the vector registers and treating them as matrices, and then do a matrix multiply using that state that's held just in the vector registers. Okay, so here what you see is you have the vector register file is feeding a matrix functional unit, but the results are going back into the vector register file, right? So that's the IME approach pursued in that task group. Now I'm going to flip to the extreme right, which is the AME attached matrix extension. So in this model, those red squares represent we added new state, new matrix state to the design. And in the case of the AME group, a large contingent in that group were interested in not being tied to the existing vector architecture and just building a matrix vector unit that was not constrained in any way by the existing vector architecture, right? And so in that case, we call this the separate matrix approach, right? It's a separate matrix engine sitting out there. Now, another thing that there was another community was interested in approach that did rely on the vector extension and added matrix state. So that one's in the middle. I've sort of labeled here vector matrix or VME. And this idea is the operands come from the vector registers but are fired into a matrix engine that's basically an outer product array doing the computation. So this one leverages the existence of the RISC-V vectors to do all the vector operations, but then launches into a matrix engine to do the matrix multiplies. So, so these 4 approaches, when we surveyed, if I ignore the vector extension one, which is really sort of vector, the 3 matrix operations, when we did a survey, we found pretty even support for those 3 categories of matrix operations. So for now, we're pursuing all 3 of these, plus the vector one as a separate extension. So there's 4 choices here. Let's just review these. So dot products, view this as being small and effective at smaller vector lengths. And it's also, it overlaps with requirements from we're seeing in the DSP space as well. It doesn't really scale up to the biggest performance with large vector lengths, so that's why it's not sufficient to cover the whole space, right? But this we see as a useful addition, and that'll, like I said, that'll be handled separately as a vector extension. So for the matrix extensions, we have this matrix in vector approach, map the matrices into vectors, no additional state. And this will continue to be pursued in the IME task group as the IME approach. The vector matrix, the proponents here are likely to create a new task group, the VME task group, which assumes you add the matrix state to a processor with existing RISC-V vector units. And this will maintain the vectorized, say, a memory model along there. And it's kind of a good match to the application processor space. We want to add a matrix unit that in the application processor space, you're already mandated to have the vector unit. So you kind of want to reuse it in this application, but get the big performance boost from having the matrix state there. And finally, the separate matrix is really unconstrained. And this is for very high performance systems where people want to focus on building a very large matrix engine that's decoupled from the vector unit completely. So this is where we are with the matrix extension group. So, and work will continue as we go forward. Very lively but constructive discussions going on in these groups. Okay, just to wrap up. So, summarize what I said. So I think for RISC-V, after this first 15 years, kind of the foundational components are in place. So a general computing platform generally has all the features you need in most places. And it seems to be working well. Like when people evaluate it, it seems to be a fine architecture for most of the work that people try with it. Now, as we move into these verticals, we're faced with the challenge of filling out those ecosystems to really be successful in each of those verticals. And we have to really engage with the ecosystem partners in each vertical. At the same time, we have to engage across the verticals to make sure we're not doing redundant work. And we're really factoring out the common modules across all of RISC-V. For AI, we think RISC-V is really well suited to AI, both current and future needs. It's nice. It's a single ISA that can handle any balance of scalar vector matrix. We have a lot of the matrix extensions, probably get a lot of highlight, but that's only one piece of the story in AI. But we have been having a very lively but constructive discussions there. So stay tuned for that. Okay, that's all I had to say. Thanks.
So we're taking questions at this time. Any questions on the topic?
Yeah, everybody's happy. That's good.
Yeah, they didn't understand my voice in this case.
Yeah, Philip was saying, are there any questions? We can take a few questions. Nope, I think we're good.
Well, in that case, thank you, Krste.